Hello everyone, this is GeoPCB, your trusted PCB partner. Today we will be introducing why understanding the structure of a four-layer board is necessary. In our previous video, we discussed in detail the importance of PCBs as the core of electronic products and took an in-depth look at the most basic double-layer PCB. Double-layer boards, with their low cost and simple design and manufacturing process, perform excellently in many simple low-frequency applications such as basic LED driver boards and remote control circuits. However, as modern electronic products move towards miniaturization, higher integration, and higher frequencies, the limitations of double-layer boards have become increasingly apparent. This is a four-layer board, while the one we introduced in the previous lesson is a double-layer board. Why can't double-layer boards meet all requirements? There are several core limitations. First, limited routing space. Double-layer boards only have a top and bottom component side. For complex circuits with a large number of components and high pin density, such as chips using BGA packages, the routing space is quickly exhausted. This often results in an inability to lay copper traces or requires a large number of vias and jumpers. Second, signal interference issues. In double-layer boards, signal lines, power lines, and ground lines are often interwoven on the same routing layer. This means there is a lack of a continuous low-impedance ground plane to serve as an ideal return path for signals, making it easy to form large current loops. As a result, crosstalk, interference between adjacent signals, increases, leading to degraded signal integrity, signal reflections, overshoot, undershoot, and other distortion phenomena. This also causes power integrity problems, such as high power noise and unstable power supply. When designing this circuit at the time, it was specifically to ensure the integrity of the analog ground on the bottom layer. A lot of optimizations and adjustments were made to the circuit to achieve this. If it were a four-layer board, then this issue would hardly need to be considered. I would just need to create a complete ground plane in the inner layer. So these are some of the shortcomings of double-layer boards. Third, they are not suitable for high-speed circuits and electromagnetic compatibility challenges. Due to the aforementioned signal and power issues, double-layer boards are difficult to implement controlled impedance transmission lines and cannot meet the strict requirements for signal quality in high-speed signals, such as those above 400 MHz. At the same time, the lack of an effective shielding layer also results in higher electromagnetic radiation, making it difficult to pass stringent EMC certification. It is precisely to overcome these limitations that engineers began to use multi-layer PCBs, among which the four-layer board is the most common and cost-effective design choice. So how does the four-layer board solve these problems? The key lies in the addition of two internal layers, with each layer assigned a specific function. The most typical and also the most recommended four-layer board stack-up is signal layer, top layer, ground plane, power plane, and then signal layer, bottom layer. Let's take a look at the example we just mentioned. Let's look at the motherboard. Its layer structure also starts with the top layer, which is a signal layer. Most of the components are placed here, and the signal traces are also routed on this layer. Then the second layer is a ground plane, which is a layer with almost no traces. The third layer is the 3.3V power plane, and it also has almost no traces. The fourth layer is the bottom layer, which is also a signal layer. Most of the traces are here, and ground copper core has also been applied. Next, let's look at its specific structure. The first layer, the top layer, is usually where the main components are placed, along with the layout of the fastest and most sensitive signal traces. Then, right next to the ground layer, the top layer and the ground plane are adjacent. Most of the components, especially the core and high-speed ones, are placed on this layer. We can also see from the 3D diagram that this is the effect of the top layer, where the core components are placed. The bottom layer holds some interfaces and a memory chip. Next, the second layer is the ground plane, which is one of the most critical layers. It is a complete, continuous copper layer that serves as the reference potential for the entire circuit. It provides a low impedance return path for all signals and effectively absorbs noise. Now, in the 3D diagram, we can no longer see this intermediate layer. This is just a ground plane, and as we can see, it has no traces, only vias and ground connections. Then the third layer is the power plane. This layer is usually a complete or segmented copper layer used for power distribution. It is adjacent to the ground plane, and together they form a large decoupling capacitance, which plays a significant role in stabilizing the power supply and suppressing noise. That is, the third layer in the middle. Since the second layer in the middle is ground, the third layer is the power plane. We can also take a look at this power plane. It is also a complete plane divided into 3 sections. As you can see, most of it is 3.3 V, and through the network you can see the 3.3 V power supply. In the middle there is also a 5 V power supply, and then another 5 V power supply for the DAP. So all the power supplies are on this layer. This is what was mentioned. If this board only had one type of power supply, then it would be a complete plane. If there are multiple power supplies, the power plane will be divided. The fourth layer is usually used to place secondary components and to route non-critical, lower speed signals adjacent to the power plane. In our case, this is the bottom layer, which only has 2 memory chips, an interface and an SD card interface. This kind of signal ground, power signal stack up, is the result of optimized design. It's not just about adding more layers. By introducing dedicated ground and power planes, it fundamentally solves the electrical performance issues of the circuit board. Today we discuss the limitations of double-layer boards and introduce the concept of 4-layer boards along with their typical stack-up structure. We can see that by introducing ground and power planes, 4-layer boards lay the foundation for addressing the challenges of high-density and high-performance circuits. In the next lesson, we will explain how these planes in 4-layer boards significantly enhance the electrical performance of PCBs, as well as when and where we should choose to use 4-layer boards. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.